Welcome to the chunk on multi-layer stacking. While single-layer stacking trains one meta model on base prediction, multi-layer stacking repeats this idea across several levels. It works as follows. We train level 0 base models, and then we train one or more level 1 models on the level 0 predictions. We use those again to create new metadata to then train a final model on the level 1 predictions. And in principle, this can be extended to deeper stacks. This originates from StackNet, which was a popular machine learning approach on the Kaggle competition website, particularly for tabular data. You can see here a particular StackNet example with 3 layers that was used for one competition, and it won that competition. You can see that on the level 0, there are many different base models from different families that are then condensed by 4 layer 1 models, and then a final random forest is used to make the final prediction. Now you might wonder, how should we train this StackNet? The first important thing is that we need to use out-of-fold predictions to train the meta models, so the models at later layers. The architecture could be optimized, but it was actually chosen manually, although this is somewhat has some analogy to training a neural network. We have multiple nodes, these are the individual models. We have multiple layers, these are the different layers in the stack model, and we have the connections, which can be seen as weights, although these are unweighted in this case. And you can see this here in this figure. On the left-hand side, we have the normal mode, which already looks like a neural network. And on the right-hand side, we actually have the so-called restacking mode, where we also have skip connections, and the neurons or the models in layer 1 are directly connected to the output model in layer 3. How should we select the models? So for base models, we could actually select them manually. We could also use evolutionary search, although this becomes a very expensive problem as we have to select all models at the same time. Because if we change a model in layer 0, it affects all models in layer 1. Then we could also use genetic search, genetic programming. We could use meta-learning to actually meta-learn which models to use at layer 0. And the same authors have already established that it's a good heuristic to reuse the same models or same model types in layer 1 as used in level 0. So the meta-learning approach just applies to both levels or even more levels. As a combiner, we could use greedy ensemble selection. So you have 2 stacks of models, and then in the end you put greedy ensemble selection in order to make a final prediction. One could use logistic regression or any other machine learning model to actually obtain the final prediction. For example, a random forest as seen here in the StackNet example. Unfortunately, multi-layer stacking also has several drawbacks. The training cost grows quickly with the number of levels, models, and folds that are needed to obtain the out-of-fold predictions. It also increases the number of design choices. We now have the depth of the StackNet model. We have model types, so which model to use in the individual layers, whether to use restacking or not, and how to choose the combiner models. On top of this, all of the different models also have their own hyperparameters. We have a higher risk of overfitting if the out-of-fold predictions are not handled carefully, and the whole thing is harder to interpret, debug, and maintain than either single layer ensembles or single models. You can imagine like you have already a random forest which is somewhat intelligible, then you combine it with a neural network, and then you feed those predictions into yet another neural network. This will become really hard to understand in case of failures. And unfortunately, there are no theoretical guarantees that adding layers leads to improved performance. The gains can saturate or even vanish in practice. Despite these drawbacks, multi-layer stacking is actually really successful in practice, as demonstrated by the tool AutoML. AutoML was presented in 2020, and since then is among the best AutoML tools that is out there. And it builds on the idea of multi-layer stacking. It used to only use the default configuration of models, but in later versions, the tool actually uses meta-learning in order to figure out what are good and complementary configurations that should be used in the assembling and stacking procedures. It applies multi-layer stacking, although not restacking, and it combines the final layer models via greedy ensemble selection. Here I've shown you a graph from the validation in the original 2020 paper, where it already improves over a lot of baselines and also outperforms the tuned random forest, a single model baseline, strongly. And the authors of AutoML have ensured to update the AutoML system over time, so whenever there were improved base models out there, for example, a new version of, let's say, a gradient boosting tool, they added it to AutoML, and so AutoML improved over the years because the base models were improved, but also because the multi-layer stacking procedure was fine-tuned for the data that is actually out there. To summarize what we've learned, multi-layer stacking repeatedly learns combinations across level. The design choices for higher level models strongly affect the performance. And AutoML is a practical example of stacking plus greedy selection that actually performs really well in practice and is used across Amazon for their machine learning tasks. Thank you very much and see you in the next video.